Alright, here's a What the Physics video about electrostatics. Specifically, we're going to be talking about electric potential energy and electric potential. Delicious. So, because it is a type of potential energy, what I'm going to do is I'm going to express this in comparison to gravitational potential energy. I could also compare it to spring potential energy as well, I guess, but in that it's something, the energy is kind of stored in there, but I think it's best with gravitational. So, yeah. Um, Electrical potential energy, some call it EPE. Your textbook refers to it as UQ, which is kind of fun to say. The Q is standing for charge here, and that is helping us distinguish it from saying U sub E, because maybe some people might get confused. Instead of thinking electrical, they'll think of elastic. So instead of like spring, whatever, I don't know. So the textbook references this in terms of launching a charged cannonball. So we have this cannon, and here's our system here. We have a cannon, and it's got some electrical potential energy because this is charged. We can see it's positive charges and positive charges right there. It's got zero gravitational potential energy because this is the 0 point, and it's got zero initial kinetic. Okay, so here's our bar charts as we've been doing before. Zero kinetic, zero gravitational, zero elastic or spring potential energy, because no springs. It's got a bunch of electric potential energy, and there's not going to be any outside work being done. We launch this, and it goes, woo! And at first I was a little bit confused, like what these little, I don't even know what those are supposed to be, but I think it's supposed to be like action lines, as in like, zoom, there it goes. So, I don't know. As it's going upwards, what is happening? Well, the fact that it's going upwards means it's gaining gravitational potential energy. The fact that it's moving means it has gained kinetic energy, and in the process it has gotten farther away from the charges, so that means it is losing electrical potential energy. Okay, so once again we're going to be able to deal with conservation stuff. So similar to gravitational potential energy in that it's a form of energy, it's going to be in joules. But with gravitational potential energy, we're always talking about lifting an object upwards, or pushing it downwards, I suppose. But we lift an object of a certain mass up a certain height in a certain gravitational field. We got mg delta h. And we could make it a little more generic with this whole equation thing here. Big G, big mass, little mass, divided by r. We know for gravitational force it was divided by r squared, right? But then we multiplied by the distance, and that distance cancel out that r. Okay? UQ does not care about mass. It does not care about gravitational field. It does care about charge, and it does care about electrical field. And as I mentioned, the units are joules. So imagine here we have this person with, I guess, a really largely charged object here, and we're bringing it closer and closer. So we start off with a particular distance r, and we bring it closer and closer, and we can see what the change in r is, and we can see what the increase in electrical potential is. The closer you get these two positively charged objects together, the more work has to be done. Or I should word that differently. You have to do more work in order to get these objects to get closer together. Okay, so I guess I should have said the more work has been done getting them together. Now, another big difference with gravitational and electrical. Gravitational is always attractive. Electrical can be attractive. It can be repulsive as well. Oop, too far. Okay. If we have two like charges, it's going to require positive amount of work for you to get these closer together. If you have unlike charges, remember they're going to be attracted to each other. So the tough part here is you bringing them apart. So this one, and these came from textbook, this one is the same shape as this one, except you can see that one is clearly positive, one is negative. Same basic equation and same basic result. The farther away, the less the absolute energy is going to be. The question is it going to be positive or is it going to be negative? Well, that depends on if they're like charges or unlike charges. Okay. Very similar to with electrical forces. If you multiply the two charges together, if they're like charges, whether or not they're both positive or both negative, they're going to be a positive result. So that means it's going to be greater than 0, right? This is going to be larger than, it's going to be a positive value. If one is positive and one is negative, then the U has to be negative, right? So just keep that in mind. But also focus on, is it easy or is it hard to move these close together, farther apart? Okay, so that's electrical potential energy. That is in joules. That is the work done getting a particular object a particular distance. Then there's electrical potential, which is different from electrical potential energy. Okay? Leave out the word energy. It is different. You can also simply refer to it as voltage, or V. So V is the amount of electrical potential energy per charge. We had actually discussed this when we were talking about when we were first introducing voltage when we were doing the electricity unit. So I'm just kind of coming back around and reinforcing the basic concept. Okay. Just like electric field, it is independent of test charge. Okay, so we divide out the Q0, and the only important charge there is the big one. Okay, and it's got some other similarities and differences among the equations we've seen before. I'm going to point those out on their own slide. Okay, the unit is joules per coulomb. You could also call it the voltage. Nice thing about electrical potential or voltage is it is a scalar, which is a little silly because the symbol is V, and you'd say, oh, V for vector, right? Sorry, that's not the case. It's not V for vendetta either. It is a scalar. Okay. Now you do have to pay attention to if the charges, if we're talking about positive or negative charges, that's the big charge. But otherwise, it is a scalar. You just say like, oh, what's the voltage here? What's the voltage there? What's the voltage for this guy over here? And you can just add them all up or subtract them if negative. But you don't have to worry about, oh, this is at 30 degrees and such. So, very nice. Here's an example problem. Why don't you try this out for a moment? So this is a little image of the heart. We got negative Q over here and positive Q over here. We don't have actual values, but we're just, doing a comparative. And we're trying to figure out what the voltage is going to be at point A out here. So that's going to be distance d from the positive q, distance twice d from negative q. Okay, so try that bad boy out, please. Okay, so hopefully we've got our equation is going to be the total voltage is just V sub positive Q, as in voltage from the red guy right here, plus V sub negative Q, that's from the blue guy right here. Okay, so my equation is K times the big charge giving off the field divided by the R. Okay. Now for the red guy, that distance is just going to be d. For the blue guy, that's going to be twice the distance. Okay. So I have these guys. And then all we have to do is add these like they're regular numbers. So notice I do have, this is, the positive Q is divided by just plain D. The negative is twice D, so I do have to have common denominators. Okay. So I'd have twice K plus Q, or I'm sorry, positive Q divided by 2D plus K times the negative Q, so you end up subtracting there, divided by 2D. You end up with this guy here. Okay, hopefully makes sense. Just some algebra there. Cool. Right. All right, so that's an example problem for electrical potential energy. Or, excuse me, I made the mistake. Electrical potential. But you might be saying, I don't really get what electrical potential is. Well, all right, well, let's go ahead and talk about it some more. The idea with gravitational, because I'm going to make this comparison first. The idea with gravitational is how hard is it, regardless of your mass, to climb a certain height in a certain gravitational field. Okay, so for example, I am more massive than most any of my students. So it is actually me doing more work to climb the stairs than for you to climb the stairs. Same number of stairs, same gravitational field, same change in height. Okay? Then again, climbing stairs is, I wouldn't say really challenging for everyone, but it's, I'd say maybe difficult for everyone. But climbing a mountain, that's going to be a lot harder than just climbing the stairs, yes? Okay? So this is, okay, people are sitting here nodding like, ooh. I'm like, okay, we are recording this, so if you could be like, I concur with that statement, Mr. Fair. That is a truth. Thank you very much. Yes. There we are. All right, people are here. Excellent. Yes. Yes. Okay. Let's see. Thank you. Oh, the Spanish-speaking contingent is here as well. Thank you. Wee! Height. Okay, great. Oh yeah, the whole multicultural group. And anywho, we all recognize it's harder to climb up a mountain than it is the steps at the high school. Yes? Yes. Okay. Yes. All right. So regardless of what your mass is, what?
The third floor is pretty high.
The third floor is pretty. Okay. Yes. Okay. But regardless of what your mass is, it's going to be harder for you to climb up a mountain than it is to climb up to the classroom, right? Okay. That's what we're getting at. It's saying, let's ignore a particular mass, or in the case of electric potential, let's ignore the particular charge. How difficult is it to go from point A to point B? Well, the larger that distance is going to be, the harder it is. So the more potential there is. And the larger the field, whether it's gravitational or electrical, the harder it's going to be. So climbing a mountain on the Earth is certainly going to be very challenging. If you move that mountain to the moon and, you can breathe and stuff like that, it's going to be easier because the gravitational field is easier. It's smaller, right? Okay, so we're ignoring specifics about mass or charge. Climbing from the first floor to the second floor, regardless of your mass. That's gravitational potential. Okay? All right. Voltage doesn't care about the test charge. Doesn't really matter how big your test charge is. All we're really caring about is the charge giving off the field. We represent that as a big Q. So as I was saying in terms of the distance, okay, if this is the big Q, I don't really care if this is 1 electron or 2 electrons or 5 electrons or whatever. Okay? For electrical potential energy, I would care, but for electrical potential, I don't really care. The idea of bringing this closer to or farther away from, that's what we're talking about in terms of electrical potential. Okay? So it's going to be harder to move at 30 meters than to move at 5 meters. Okay? And on the topic of climbing the steps you might consider hard, you might consider challenging. Okay? But then walking around on the second floor or the third floor or whatever floor, that's not so difficult, right? Okay? Because you're not going up, you're not going down. We consider that an equipotential. So think in terms of the distance that you're going up or down in the gravitational field. If you don't have to go up or down, we're all going to be at the same gravitational potential. Likewise with electrical potential. A charge at point A, point B, point C, they all have the same electrical potential. They can move around in a circle, and that's no big deal at all. But if they tried to move to a different circle, well, then there's going to be work done. Positive or negative, it depends, but then we're doing work. Okay, if you think of a contour map, which some of you might be saying, what's a map? I just use Waze, or I just use, whatever. They just tell me to turn here. Okay? The GPS of some kind, right. Okay. Well, there's these things called maps. Okay, and if you look at contour maps, this is like an above view of some hilled area. This would be the side view. Okay, and these lines here are all the points along here at a particular elevation. So walking around at this particular elevation, that's like walking around on the second floor, or walking around on the third floor. Going to a different loop, that's when you're going to be doing work, positive or negative. Okay? And the closer these are together, the steeper the slope is going to be. So if I were to draw equipotential lines as well as field lines, the equipotential lines are the dotted areas, and the field lines are these guys here. It's like the path to move in closer or farther apart. Whereas the equipotentials, those are the constants the whole way through. Okay? Good stuff. As I told you, I'd like to compare the 4 different equations. This is the one for electrical force. Unit is the Newton. We talk about both charges, and the distance is squared. This is the one for electrical field. We do not care about the test charge. It is newtons per coulomb. but both, I'm sorry, it has distance squared. Both of these are vectors. Now, for electrical potential energy, it's joules. Okay, as we said, all we're doing is taking the force, multiplying by a distance. I mean, in a particular direction and whatever. But we get this, so that's why one of the r's is canceled out. So both charges, but it's just distance, not distance squared. And then this is voltage, or electrical potential. We only care about the big charge. It's going to be in volts, and it's just the distance. And these guys are both scalars. So I set them up in this particular order so you can see comparisons vertically, but also horizontally. You go horizontally by multiplying or dividing by R, right? If we're talking like work, change in energy. Work is force times distance, so it's easy to go across there. Well, likewise with this. This is electric field times the distance, and we get electric potential. Okay? So hopefully that helps to distinguish it, because I know it can get rather confusing. Okay? Okay. Delicious.